A battery consists of variable number n of identical cells having internal resistance small r each, which are connected in series. The terminals of the battery are short circuited and the current I is measured. Which of the graphs shows the correct relationship between I and n? So I is the current that is going to flow in the circuit and n is the number of cells. In series, the current will be same, the potential will be divided. So we have a series connection of n cells, so there needs to be a single current, and the formula for series connection, I think I had given while discussing the derivation of series combination. It will be n times of epsilon divided by r plus n times of the resistance. Because it is n cells, the EMF is going to be multiplied n times, and also the internal resistance that is going to be multiplied n times, and this was my general equation for a single cell. But here we have got a series connection of n cells, so even the EMF is going to be multiplied by n, and even the internal resistance is going to be multiplied by that. There are n cells, so n I have written already there. There will be n times of internal resistance. What is the external resistance? Because what is given in the question, there is a special word, short circuited. Short circuited means there is no external resistance connected across the terminals of the battery, only there is a wire which is connected to the two terminals. So it is a short circuit. Short circuit means there will be no resistance, so I can take that R as 0. So it will be n times of epsilon divided by 0 plus n times of R. So it will be n times of epsilon divided by n times of R. N goes out, what is left is just epsilon divided by R. So that is my current. Is there any relationship between this I and n in the right hand side? There is no n appearing in this part of the equation. That means there is no dependence of this current on this n, that is the number of cells, is not going to change the current. So there are 4 graphs given in the question. First one is a straight line, the second one is again a straight line, the third one is exponentially increasing, the third one is exponentially decreasing. So the correct answer for this one will be option A, because the current is independent of n. That means the current remains constant. Equal resistors of value R each are connected in series to a battery of EMF. They have given it as E, they could have been epsilon also. So, and internal resistance capital R. Now look for those two letters. The external resistance, that is also R, and the internal resistance, that is also equal to R. So internal resistance and external resistances both are equal to R. The current drawn is I. Now the n resistors are connected in parallel to the same battery. Then the current drawn from the battery becomes 10I. The value of n is, what we have is, the resistors are connected in series, so I will take it as Rs. The resistors are same, that means I am going to take it as n times of R. And also what is given here is the internal resistance is also equal to R. So if I take the equation for the current, or this is the correct equation for the current, so I will be equal to epsilon divided by R plus R. So what will be these R? This will be Rs, and this small r will be this thing, so I can write that epsilon divided by Rs is n times of R. Then there is R, small r is again equal to R. So if you look into the denominator, I can take that R common. So this will be epsilon divided by R is taken common, it will be n plus 1. Question number 1. So this is for the series combination of n cells connected, and such that there are n resistors in the series combination, and then there is a single resistor, internal resistor of the same value connected to the same setup. Now going for the RP, that is the parallel resistors. When I have the parallel resistors, what I had said while deriving the equation, if I got n resistors in parallel, the total resistance will be R divided by n. Now again the current equation will be same. I will be equal to epsilon divided by, here it will be Rp plus R. If I substitute this Rp, so it will be epsilon divided by R by n plus that small letter r is again capital R. So I can take this, the LCM of this thing, so it is going to become n times of epsilon divided by, this n is going to appear here, so again it will be n plus 1 time of R. So this is my current. Now what is this current for the parallel combination? I could have taken it as I dash. So that I dash is given as 10 times of I. So I can write the 10 times of I in the place of this I dash, because this was series combination, current was just I. When it became parallel combination, the current changed to 10 times of I. So I can write it as 10 times of I equals n times of epsilon divided by n plus 1 into R. Now what I can do, I have two methods. One thing, that's equation number 2. One thing I can do here is, I have the value for I as epsilon divided by R into n plus 1. I can substitute this I in the place of this I, or alternatively, I can divide these two equations. So I will divide that equation 2 divided by equation 1. So it will be 10 times of I divided by I equals n times of epsilon divided by n plus 1 time of R whole divided by epsilon divided by, it will be R into n plus 1. So that is inside the bracket. So I hope you are able to see that. So there is a R into n plus 1, there is a R into n plus 1. These two will cancel out. Epsilon and epsilon will cancel out. On the left hand side, I and I will cancel out. What I am left with is only n equals 10. So the answer for the question is n equals 10.